I'm going to make a quick video on the beginning of section 2.6 because I already have videos posted on examples 2 and example 3. Sorry, examples 2 and 3. So I wanted to make a quick video for you guys to introduce the material so that you understand what we're discussing in the other 2 videos. I had made those previously. I think it must have been last summer or the summer before. I had already made those. So I wanted to give you an introduction to section 2.6 on the nonlinear integrating factor. So if you remember when we were in class yesterday, we talked about how we can sometimes take a non-exact equation and we can make it exact by determining a nonlinear integrating factor and multiplying. I mentioned that we could do this. So we're going to look at this one and see what happens and how that works. It's very, very similar to what we did in section 2.1 with the linear integrating factor. So for example, the example I gave you here, we have 3x plus 2y squared dx plus 2xy dy. And we said that one is definitely not exact. Well, if we look at it, let's look at m sub y would be, well, the 3x, its partial derivative with respect to y would be 0. And the 2y squared would become 4y. And if we look at n sub x, because remember this is our m of xy, and that's our n of xy, well, n sub x would just be 2y. So those are not equal, so this is definitely not exact. So what happens though is if we multiply everything by x, it does become exact. So if we look at it now, m sub y here is now 4xy, and n sub x is now 4xy. So how did we know to multiply by x? That's what we're looking at in this section. So a function mu this time is now going to be a function of x and y. When we looked at linear integrating factors in section 2.1, we focused specifically on mu of x. We looked at a function of only x. Now we're going to look at a function of x and y. And if you'll notice here, we're going to be multiplying both the m by mu of xy and the n by mu of xy. And of course, 0 times mu of xy is still going to be 0. So we're doing the same approach that we did in section 2.1. It's just that now we're finding a multivariable integrating factor instead of a single variable integrating factor. So how do we find this nonlinear integrating factor? So if we know the functions exist, how do we find it? Well, we have options. We can either find m sub y minus n sub x and divide it by n. If that is independent of y, meaning it's only a function of x, then we can find p of x as being the partial of m with respect to y minus the partial of n with respect to x, which are the 2 partial derivatives that we find in any case to detect whether it's exact or not. So we've already determined what they are when we do a problem. So we'll have those, and then we can divide by the function n. If that comes out as only a function of x, then we can use that as our e to the integral of p of x. So you notice then we would have an integrating factor here that would be just mu of x. Now, if we find that n sub x minus m sub y, so we subtract them in the opposite order and divide by m, and we get only a function of y, then we can say that mu of y is then plus or minus e to the integral of q of y dy. So we have 2 different options. So much like when we looked at exact equations, and we had 2 different paths we could take for our integration, where we could start with m or we could start with n, we have the same idea here with these nonlinear integrating factors. We can check for either one. Sometimes we'll only get one of them as a function of a single variable and not the other, but sometimes both of them will work. So you have options. So let's look at the only example that wasn't covered in other videos. So I shrunk the page a little bit here because I know I'm going to need a little bit more space, but I wanted to have a look at this problem. And so if we look at m of xy here, and we have our n of xy here, let's start with determining whether this equation is exact or not. So if you remember, we do m sub y, the partial derivative of m with respect to y. So we would end up with 6xy squared minus, well, 3 times 2 is 6 again, x cubed y squared. And then we would have 4 times 2 is 8, so minus 8xy, and then the 2x would be 0. And let's look at n sub x, the partial of n with respect to x. So we would get 3 times 2 would be 6x y squared, and the partial derivative of 4y would be 0. So clearly, m sub y does not equal n sub x. But we will need both of those expressions here. So we know this is not exact, but let's see if we can find a nonlinear integrating factor. So we can do p of x, which is going to be m sub y minus n sub x all over n, or we could do q of y, which is going to be, switch them around, n sub x minus m sub y, and now divide by m. In this case, I will say I chose p of x, and I'll show you why. So if I chose p of x, so I said let's take 6xy squared minus 6x cubed y squared minus 8xy, and then I'm going to subtract from it the 6xy squared. So those 6xy squareds cancel out. So that'll work out fine. So these guys will cancel out. And then we divide it by n, and n here is 3x squared y squared plus 4y. And something really cool happens here when we look at this and we simplify it. Because if we factor out a negative 2x from both terms here, we end up with 3x squared y squared plus 4y. And then on the bottom, we have the 3x squared y squared plus 4y. So again, these guys are going to cancel out, and we're simply left with p of x equaling negative 2x. So now we have a nonlinear integrating factor, mu of x, that's e to the integral of negative 2x dx. And the integral of negative 2x is just negative x squared. So we get e to the negative x squared. And we can do plus or minus, so we'll choose the positive. I always choose the positive. So let's do e to the negative x squared. So now we've got e to the negative x squared times 2x y cubed minus 2x cubed y cubed minus 4x y squared plus 2x dx plus e to the negative x squared times 3x squared y squared plus 4y dy, and it equals 0. So now here is the cool thing, is now if we start with n this time, we know then that n is the partial derivative of our solution with respect to y, and that would be e to the negative x squared times 3x squared y squared plus 4y. And I chose that one simply because it's shorter, as funny as that sounds. So if we wanted to do our partial integration here, we could, because this was the partial derivative with respect to y. So that e to the negative x squared was already treated like a constant. So when we integrate to get to f of xy, e to the negative x squared still just comes along for the ride. And on the inside, we just have to integrate with respect to y. So we would end up with x squared y cubed plus 2y squared. And then we'll have possibly some phi of x. So if we were to multiply this guy out, we would end up with x squared y cubed e to the negative x squared plus 2y squared e to the negative x squared and plus some phi of x. And now, as we know, the next step then would be to take our function here and now integrate with respect to the other variable. So we already, or sorry, take our derivative, not integrate, sorry about that. I misspoke. So we already integrated with respect to y, so now we'll differentiate with respect to x. So let's find f sub x. Well, now we got to look at here, we've got two functions, so we're going to need a product rule. So 1 times the derivative of the second would be negative 2x e to the negative x squared plus the second times the derivative of the first, which would be 2xy cubed, and then the derivative of 2y squared, that comes along for the ride, and would be negative 2x e to the negative x squared, and then b plus phi prime of x. So this is where things get a little interesting, because all we have to do now is we need to show that if we factor out this e to the negative x squared, we should find that we have negative 2x cubed y cubed, right, plus 2xy cubed minus 4xy squared plus phi prime of x. And now we need to set this equal to the e to the negative x squared. And it just reminds me, I forgot that this should have been mu of xy here times n, because this would be equal to, we're going to set it equal to mu of xy times m. So we're going to set it equal to e to the negative x squared times 2xy cubed minus 2x cubed y cubed minus 4xy squared plus 2x. And a really interesting thing happens in that almost all of these terms are going to cancel out. So the negative 2x cubed y cubed is gone, the negative 4xy squared is gone, and the 2xy cubed is gone. So really, all that we're left with is phi prime of x on the left is going to be 2x e to the negative x squared on the right. So if we were to integrate here, you could do this by parts if you wanted to, but you can also see that negative 2x is the derivative of the negative x squared. So literally all we have here is a negative e to the negative x squared by the chain rule. So in that case, now we know what phi is. So we can say then, we know now that f of xy is going to be e to the negative x squared times x squared y cubed plus 2y squared minus, so plus phi of x, which is now minus e to the negative x squared. So therefore, our solution is that we're going to set this equal to c. So we end up with e to the negative x squared times x squared y cubed plus 2y squared minus e to the negative x squared is going to equal c. And I'm sure we could probably come up with some sort of an explicit solution somehow, maybe, but I'm okay leaving this one as an implicit solution. So this should help get you started on the path to finishing up example problems 2 and 3 in the other two videos that I made previously.